So this is my sixth lecture today, and I'll be talking about the basic tests of static quark model and also color hypothesis. And these are the various subtopics which I'll be covering today, along with giving you a very brief idea about the heavier quarks. And in this page you can see the various topics which have been covered in my lectures so far, including the last lecture where we have a detailed discussion on the overall course, and I have used my website to discuss about these topics, and also we have discussed the question bank 1 on the quark model, and this question bank basically covers the lectures up to this 1A, 1B, 1C, 2 and 3. These are the parts which have been covered. The fourth lecture, which was on the color of quarks and exotic hadrons, and also today's lecture, I'll give a separate question bank based on them later on. So with this, let me start with today's lecture. So these are the four topics which I'll be covering today. Well, let me start with the first topic, which is the baryon magnetic moment. Now you see what we have done so far. We have talked about the various details of the static quark model, and now let me talk about some of the applications and which we will try to compare with the experiment and see if indeed quark model is good enough. The first application here is the calculation of baryon magnetic moment. You see, the experimentally measured values of the anomalous magnetic moments can be explained in terms of the magnetic moment of the individual quarks and the baryon wave functions, which we have calculated in the previous lecture. Since quarks are fundamental Dirac particles, the operators for total magnetic moment and also the Z component can be given as this. And with this, let us see what we can do. So for the spin of quarks, the expectation value of the Z component of the magnetic moment for the up and down quarks can be written as this, you see, and this is the expression. Fine. And the corresponding expressions for the spin down quarks can be calculated in a similar fashion, and these are the results. Now, the total magnetic moment of a baryon, which consists of 3 quarks, right, is the vector sum of the magnetic moments of the 3 antisymmetric quarks, right? So I've written use the indices 1, 2, 3, and so mu I is the magnetic moment operator which acts on the ith quark. As a result, the magnetic moment of proton can be written as here mu p. I have used the proton up spin wave function, and then the order of the quarks appear in the proton wave function does not affect the calculation of magnetic moment, and so we will just use the first 3 parts of the entire 18 terms present in the total proton wave function, which we have discussed in previous lectures. And if we use this in equation 1, where was it? Yeah, before, and then which was this expression. If we use this here, you see the up down expressions. Yeah, here proton, it should be equation 1, 3. If we use this in equation 1, okay, so this should be equation 1, not 3. And if we use that, then using the orthogonality of the quark flavor in the spin state, which is this expression, you can work it out, and then we get the expression for the proton magnetic moment as follows. See, the 3 terms are here. Now we will use these relations which we have obtained previously, and these 4 relations, you remember, these are the here which we have obtained, and if we use these 4 relations, then here, yes, and also the one before here. So if we use these relations, which can be used using this relation and the ones over here, then after simplification we will finally get this result, which is mu p 4 by 3 mu u minus 1 by 3 mu d. The prediction for the magnetic moment of neutron can be obtained if we just replace u with d, and we will get this result here. Now what do? We assume that the masses of the u and d quarks are quite equal, and then the expression for mu u and mu d becomes mu u equal to minus twice of mu d. So if we use the relation, then the ratio of the magnetic moments for the proton and neutron becomes minus 1.5. Now you must be wondering, how does it compare with the experiment? And it is indeed remarkable that this result agrees very reasonably with the experimental value of minus 1.46, giving a great support to the static quark model. The best agreement between the quark model prediction and the measured value of the magnetic moments for the L is equal to 0 baryons is obtained with these values I have mentioned here. But you note that the results are somewhat far off, you see, and also the mass of the S quark, this is also quite higher compared to normally accepted 150 MeV. This is much higher, and if we use this, we get these values which are experimentally we get it. Now this reproduces, if we use them using these values, we get them, and if we use these 2 values mu u and mu d, then we reproduce the observed values of the proton and neutron. But there is a problem. You see, these 2 values, they are not quite same, and also the S quark is much different. Now how to resolve that? Or you can ask, what is the reason for that? But before that, let me see how this can be done. You see, what we want to do is we want to estimate the mass of quarks from magnetic moments. Now if we write the magnetic moment in terms of the nuclear magneton, I am using the H cross and C units here. Then for the U quark, if we write it as 1.85 nuclear magneton like this, and then we get, using the proton mass, this value of 338 MeV. Similarly, we will find the mass of D quark to be 322 and the S to be 510 MeV. So what do we get? As I was telling before, these calculations give the S quark mass heavier by about 180 MeV than the mean of Mu and Md, and also Mu and Md are close to each other. However, one undesirable feature is this: Mu is greater than Md, which contradicts the evidences obtained from other sources. This discrepancy is actually due to a small amount of orbital angular momentum in the wave functions, as well as our neglect of relativistic effects such as exchange current. Now with this, let me go on to the next topic, which is basically the mass of quarks. Now we know that free quarks have not been discovered and quarks in hadrons are assumed to be confined. This leads to a difficulty in estimating the mass of quark. The mass of a particle can be precisely defined by its energy only when it is a free particle. And since isolated quarks are not observed, it is quite difficult to talk about the precise value of its mass. At the best, what we can do is to refer to the effective mass, M effective, rather than the true mass. Now, the value of M effective would depend upon the interaction of one quark with another. Now, talking about interaction, did I ever talk about the interaction of one quark with other all this time? The answer is no. And why is it so? You see, what we are talking about right now is the simplest possible model of quarks, simplest possible model of hadrons made up of quarks which do not interact with each other. You see this figure A. This is precisely the static quark model. Here I am showing the proton, and this figure shows that the proton is made up of three valency quarks, U, and D, which are much lighter and smaller than the global proton mass, and also their size is smaller. The most important thing is that they just don't interact with each other. Fine. Now, actually this is not the real picture, which I will talk about in the next set of lectures. In the real scenario, these quarks do interact with each other, and that is called the dynamic quark model of hadrons. Here you see figure B, where in addition to the three valency quarks which I have shown in the previous case here, we also have many other things. And what are they? We have many gluons and many quark-antiquark pairs. And all these together contribute to the proton mass. So, and here is what I have just summarized. You see, the quark mass is quite hard to measure since we can never isolate the quark. And at lower energies, they form hadrons and the constituent mass is relevant. This is what we talk about at lower energies. However, at very high energy, the masses of quark appear very light, you see. So if the proton is made up of just UUD and its mass is just 5 MeV per c square, then where does this mass of the proton comes from, right? And I will talk about it in the next set of lectures. But this should be kept in mind, this difference. Okay. Well, even so, a crude mass of the U and D quarks can be found from the structure of nucleons. How? For very low energies, you just assume that the proton, all the mass of the proton is just due to the sum of the three quarks. And as a result, you get this mass of U quark and D quark is just 1/3 of the mass of nucleon, and so it's approximately 310 MeV. Now, for the S quark, let us consider the phi meson, which consists of S and anti-S quark, right? And so we get from the mass of the phi meson the approximate value of the mass of S quark, which is 510 MeV. Okay, so next what do we do is this. We just do a very simple estimate. We try to find the difference between mass of neutron and that of proton. And since these are the constituents of them, you see ultimately we get the mass of deuteron and we get the mass of D quark and mass of U quark, and the result is 1.3 MeV. This we get from the experimental masses of neutron and proton difference, which comes out to this mass difference of D and U quark, and this value is from experiment, right? So they are not same, they are different, right? What do you have to say? Well, we also have to remember that there is charge Coulomb interaction taking place. We have to keep that in mind. Let us estimate it then. Now the Coulomb energy difference associated with the electrical energy between the pair of quarks is of the order of E square by 4 by epsilon 0 R0, where R0 is the size of the baryon. And so if we assume it to be of the order of 0.5 Fermi meter, then we get it to be 1.4 MeV. Thus, what we get is the near equality of the U and D quark masses. Now, so far so good. However, if we assume that the difference in multiplates for the baryon, decaplet and octet, let us now concentrate on the baryon, decaplet and octet, right? Now, if we assume that the difference in multiplates arising due to the strange quark content as for the baryon decaplet, then this hypothesis gives the following results. You see, M sigma, M delta. This is where, this is here, mass of sigma and delta. Now you see, are they same? No, they are not the same. They are somewhat different. Now what about this thing? Mass of delta minus mass of nucleon here. This difference compared to, you see, this difference, and what is this? This is the average of the three sums right here. So if we assume the difference, if we compare the differences, they are not the same, they are somewhat different. And this I have done for the case of octet. What I want to show you is that there is something going on. We are observing some differences we cannot just explain. There is something more into the picture. We are probably missing something. Now let us just compare the scenario of the decaplet. You see, if I compare the sigma with delta, that means this and this, the difference is 153 MeV. Now for the other case, what is this one? This one, the difference is 145 MeV. Now we know that this difference is mainly due to the S quark additions, right? But even so, you see, you just cannot get the same result. The results are slightly varying. Now why is this so? As I have said before, even if for the decaplet we just observe small differences, for the case of octet the difference is much massive. And why is it so? Well, I've just summarized it here. The mass differences between the UDS quarks explain many of the mass differences of normal and strange hadrons. However, they are not sufficient enough to explain the observed mass differences between the members of the half plus baryonic octet and the members of the 3/2 plus decaplet. This must be interpreted in terms of the differences between quark-quark interaction and the largest contribution given by the part of the strong interaction which depends on the spin. So this is the first scenario where what I am doing is I am just using our simplest possible basic model to try to estimate and compare and see if we get the masses of the decaplet or octet correct. However, we are seeing differences and the result is some sort of residual interaction we are missing. And so what we did right now, what we are going to do is, we have till now assumed that the quarks do not interact with each other or something like that. There is no interaction. But now let us just introduce a very small interaction, spin dependent interaction. And how are we going to do that? What is the term going to be? How should the spin interaction term look like? Well, we will use quantum electrodynamics as our guide. You see, in QED, the potential energy between two magnetic dipoles contains a term proportional to scalar product of the two dipole moments, mu I dot mu j. Now for two Dirac particles of masses mi and mj, this corresponds to a potential energy term of this form. You see, U is proportional to Si dot Sj, like this, where alpha is the fine structure constant. Now this QED interaction term, which contributes to the hyperfine splitting of the energy levels of the hydrogen atom, is relatively small. Okay. Now, the meson masses we are going to estimate right now. The baryons are much harder. I am not going to talk about it today. Now, you see, the corresponding QCD spin-spin interaction in this potential form, we are just using a similarity estimate from the QED case, and let us assume this thing, where alpha is the coupling constant of QCD. Now since alpha is approximately equal to 1, is much greater than this value, the chromomagnetic spin-spin interaction term is relatively large, and it plays a very important role in determining the meson masses. Now, for the case of L is equal to mesons, you see the mass due to the meson mass due to the mass of quarks and spin couplings can be written like this: m1 plus m2 plus this spin dependent term, and I have just written it here in complete form. And now if I use these values, mu and md same, and ms somewhat different from the one I have talked about before, if we use these values and the mass here, then these are the predictions. You see, these are the predicted values for the various mesons. These are the various mesons, and these are the experimental values. And what we see here is indeed a very nice agreement between the predictions and experiments. So, compared to the previous test of static quark model, that is for the baryonic magnetic moment, here we have to introduce a small spin-spin interaction, and after that we get very nice predictions for the case of the meson masses, which I have shown here. Okay, so let me now talk about two very simple limitations of the SU3 flavor group static quark model. The first one is that although we have constructed baryons from three representations, you see 3 3 3 equal to 1 direct sum 8 plus direct sum 10, where there are two octets of baryons, one being symmetric and another being antisymmetric. In the interchange of the first two quark indices, the presence of two octets leaves the question that to which octet the observed three baryons belong. Okay, observed baryon octet, which we experimentally observe, which octet it belongs, the symmetric one or the antisymmetric one. The second one is that, you see, let us go into a little bit more deeper, which I have not talked about. So I am just going to focus it here in this case only. Now, the SU3 predicts octets of baryons and mesons. If we take the baryon octet as this basis and wish to construct a decouplet of baryons, then we can do it by this 8 cross 8 star, you see, which though provide a decouplet state 10, but also provides 10 star and another 8, We can also take octet of mesons and as the basis and may attempt to construct a 10 through this here, you see, this thing, where we get the same reduction as in expression A here. They give the same reduction, and we observe an unobserved, and we actually note an unobserved splitting of this type. So this we have not observed. So these are the two very simple limitations or drawbacks of the static quark model. Now let me talk about the third topic. Well, I did talk about the color hypothesis in lecture 4. Now, how to confirm it experimentally? Well, you see, the proposal of the quark freedom also explains the relative cross-section R for producing hadrons in E plus E minus collisions. Now, QED for E center of mass less than 3 GeV, it gives this value of R, where this summation of R being equal to summation of Qi square, where Qi is the charge of the ith quark, and we do the sum over all the quarks which can be produced at that energy. And what is R? Well, R is the ratio of cross sections for producing hadrons and for producing a muonic pair. You see, this is the ratio. Now suppose the energy for E plus E minus system is sufficient to produce all the three flavors of quarks. And right now we are talking about just the U, D and S quarks. So if the quarks are colorless, then the result is this. R is equal to 2 by 3. And if the quarks have 3 colors, then the value of R is 2. And from experiments, we do get this value consistently, which gives a great proof for the existence of color hypothesis confirmation. Now, so let me talk about the last part, and it will be very brief. You see, we started with the static quark model, and in the high energy limit, these are the two masses of U and D quarks. Now if you compare them with the mass of baryons, right, it's of the order of 1 GeV or more. Now you see, compared to them, the difference between these two is of the order of 2 MeV or so, very small. So you can say that they are almost the same, and as a result we have an approximate symmetry, SU2 symmetry, or the flavor symmetry between the U and D quarks, also called the I spin, I for isospin, right? I spin symmetry, and we get various hadron multiplets. These two UD quarks do form a very strong isospin doublet, yielding a small mass difference between the two quarks. And this strong interaction is independent of the quark flavor, and there is an almost complete symmetry between the two members of the doublet, broken only by the EM interaction. Now next enters the strange quark, whose mass is little bit higher, and as a result, even if we compare the difference with the two other quarks, the difference is much higher, but still compared to the mass of baryons, which are more than 1 GeV, right? Still they are somewhat same. You can assume that they are the same mass, and as a result, if we do this assumption, we have a somewhat badly broken symmetry, and this is the SU3 symmetry between the UDS quarks. You note that this is somewhat more badly broken compared to the SU2 symmetry, because the difference between these two is quite different from from this 3 case SU3 symmetry scenario, where the S is much heavier, right? And next is the charm quark. Now this addition to the charm quark of the charm quark leads to an extension of the family from SU3 flavor to SU4 flavor, which is even more badly broken, or I should say heavily broken, since the quark C, its mass, is much larger than the first three. You see the value 1275 MeV per c square. You see it's much higher. Even if you add the 3, its value is much higher. And so it's even more badly broken symmetry, this SU4 symmetry between the UDSC quarks. Even so, if we assume it, we can get a symmetry of I, Y and this C for charm quantum number in hadron supermultiplets. So now we have supermultiplets. Previously for SU2 we have hadron multiplets, and then for SU3 we still had hadron multiplets in I and Y, but now we have supermultiplets. And afterwards this addition of the bottom quark leads to SU5 symmetry, which is even more badly broken than the SU4, since its mass is even more than that of the bottom quark. And so a very small few lines about this discovery of charm quarks. Well, in 1974, Ting, Richter and various others, using different methods, discovered a heavy meson of mass approximately 3 GeV per c square. Its lifetime was 3 to 4 orders of magnitude larger than mesons of similar masses, and this makes it unique in particle physics. Named J or psi, it was later shown to be the bound state of a new kind of quark called the charm quark and its anti-quark. The J or psi particle decays into the charmless particles via the Oz rule or Zweig's rule, or into a lepton pair via electromagnetic interaction, and thus has a very long lifetime. You see, this is quite long compared to the standard strong interaction lifetimes, which is of the order of minus 10 to the power minus 22 to 23. Now, this discovery of J or psi caused a revolution in particle physics and led to the acceptance of Gell-Mann and Zweig's idea that indeed hadrons were composed of quarks. Well, so what do we get? You see, the structure, and how do you get that? You see, with the existence of a fourth flavor, the flavor symmetry group changes from SU3 to SU4, giving rise to more complex multiplets, which were named supermultiplets, as I have talked about before. Now, this can be visualized as solids in a 3-dimensional space spanned by I3, Y and C, where C is the new charm quantum number. You see, these are the values: C equal to 0, C plus 1, C plus 2 and C plus 3. Now our meson nonets become a 16 plate through this 4 cross 4 bar equal to 1 sum 15. Similarly, for the baryons, the 27 plate now becomes 64 plate through this 4 cross 4 cross 4 equal to 4 sum 20 sum 20 sum 20. So let me just talk about it. You see, previously when we have SU2, we just have this in cases, right? Afterwards we introduced S quark and we talked about the baryon decouplet. Okay, now it is important to note that in addition to the presented multiplets which I have talked about before as well, other baryon multiplets with higher spins were observed, which can be interpreted as combinations of 3 UDS quarks with orbital angular momentum quite different from 0, in order to obtain the observed spins of baryons. Now it is important to remember that the separate quantization of spin and orbital angular momentum is possible only in the non-relativistic approximation. Okay, so this is the scenario, right? Now next, yes, if we introduce the charm quark, then from SU3 symmetry between UDS, we go to symmetry between UDSC. Then you see this thing. This was the baryon decouplate, right? This becomes a pyramid, and with the base as the baryon decouplate. So you see a pyramid along this axis, which is the charm axis. It grows and you get a pyramid like this. So we have a pyramid with C along Z axis. And again, I have shown for the sake of completeness, I have shown the previous cases of pseudoscalar meson, pseudo vector meson, octet, and then the baryon octet and baryon decouplate, and afterwards we get this. So you see 2D, 3D, 2D, 3D, you see, and these are the values with different charm quantum numbers, you see, and this is the pyramidal structure. Okay, and this is the axis, C axis, this is the IZ and S axis. So we have SU2 over here, SU3 over here, and now we have SU4. Okay, now something very interesting. You see, this C bar states named Charconium states are particularly interesting. Why? Because they correspond to the non-relativistic particle antiparticle bound states. Okay, so what? Well, you see, the Charconium states have thus a structure of excited states similar to positronium. Now we know positronium, right? Which is an E plus E minus bound state. But their energy levels can be explained by a potential in which a linear term is added to Coulomb-like interaction, which ensures that an infinite energy is needed to separate the quark and anti-quark. And this is important since no free quarks have been observed up to now. And this is the expression for the potential, where R is the radius of the bound state, alpha S is the equivalent of the strong interactions of the fine structure constant alpha, kappa is a positive constant, and this coefficient 4/3 has to do with the color structure. So it's just important to know that the first term is of the order of minus some constant by R plus some other constant into R. Okay, now, about this linear term. Now, of course, when will this term become important? When we go to large distances. Now, whenever the pair, this Charconium, inside the Charconium, we have C bar pair, right? Whenever this pair is stretched, you see here, a field string is formed storing potential energy like this. And at some point, part of the stored energy can be converted by tunneling effect or so into mass, and a new quark antiquark, you see this quark antiquark, they are produced. Okay, this should be Q bar, I'm sorry for that, this should be Q bar, right? And after that, if you stretch it a lot in these two directions, then in between, using the sum part of the energy which has been taken in from the stretching in energy, a Q bar is formed, and we now have a new quark antiquark pair, right? And as a result, now we have got two new mesons. This process is called quark hadronization, and this plays a very central role in high energy hadronic interactions. Now, about bottom quark, very briefly. Now, it was discovered in 1977 at Fermilab with proton on beryllium scattering, where a new resonance state was found, and it was interpreted as BB anti-B state quark. You see the mass of it. It's much higher than that of C quark. It's 9.64 GeV by C square. And also, like the J psi decay, it also decays by both strong and electromagnetic force. regarding the top quark. Now it was discovered quite late compared to the other quarks. It was discovered in 1955 through two different experiments, and it decays by the weak force. Now, one thing to note, it is the heaviest quark out of all of them, and the reason of why it is so heavy, it's still a mystery. But one thing is important. You see, this quark is much heavier than a gold nucleus, and with such a large mass, its decay phase space is huge and its lifetime is very short, even if the decay is mediated by the weak force. It is so short. Now the estimated value is around 10 to the power minus 25 seconds, that the top does not live long enough to hadronize, which means there are no top hadrons. So now just to summarize, so we have 6 quarks and 6 antiquarks, and these are the baryon numbers: 1 by 3, 1 plus 1/3 for quarks and minus 1/3 for antiquarks. And we have got separate quantum numbers starting from strangeness, charm, bottomness, topness, and these are the numbers. Okay, and these are the various properties of these 6 quarks. What is important to note that the baryon number B is conserved in all interactions, and these 4 quarks, 4 numbers, right? The number of S quark, C quark, B quark, T quark. They're also, you see, this number is basically a difference between the number of quark and its anti-quark. This difference of numbers. Yes, they're conserved in strong and electromagnetic interactions. And we already know previously that I and IZ are also conserved, are both conserved in strong interactions. And so with this, I have completed today's lecture. Thank you.